big picture for the central limit theorem is that we're going to be using it when we consider a sample instead of an individual. For a group, we need to change the standard deviation to be the original standard deviation divided by square root of n, because a group will have less variability than an individual. And then we would do the calculations just as before with this new standard deviation. Let's take a look at a series of questions that can help us understand the difference between an individual and a sample. Example 1. The average teacher's salary in Connecticut is $57,337. We'll suppose that the distribution of salaries is normal with a standard deviation of $7,500. What is the probability that a randomly selected teacher makes less than $52,000 per year? We have our mean, 57,337. We have our standard deviation, 7,500. And we want to know what is the probability that a randomly selected teacher makes less than $52,000. So we're looking for the probability of x less than 52,000. If I draw my graph just like before, I'll put the mean in the middle, and then I have to determine where does this x value, 52,000, fit on this x-axis relative to the mean. And I see that 52,000 is less than my mean, so I'll put it to the left. And I want x less than that number, so I want the area to the left of 52,000. The area to the left of 52,000 would be norm.dist. Remember that the norm.dist function gives us areas to the left. So we'll put in our x, 52,000. Include our mean, 57,337, standard deviation, and true, always true. And let's work this in Excel. Keep in mind that the formulas we're using in Excel are exactly the same formulas and syntax order that we would have in Google. Norm.dist, 52,000, 57,337, 7,500, and true, and our probability that we get is 0.238 or 23.8%. Notice a randomly selected teacher, my n is 1. I only have one randomly selected teacher. This example is really from section 6.2. This would be something that we would do, generally speaking, for a normal distribution. But now contrast that with example 2. We're going to have exactly the same setup. The mean is 57,337. My standard deviation is 7,500. This time we're sampling 100 teachers' salaries, and we want to know the probability the sample mean is less than 52,000. So a little bit of a different setup. Now instead of the single individual x, we're going to use the sample mean x bar. I also am going to include that n is 100. We're sampling 100 teachers' salaries. This means that when we're inputting our calculation, instead of using the standard deviation, we're going to use the standard error. So here's what I mean. We'll have the same graph as before, and we're looking for the same probability to the left. But when we go to the norm.dist function, we don't want sigma, we want the standard error. And the standard error is given by sigma divided by square root n. So we're looking at 7,500 divided by square root 100, which would be 10. And we have a much smaller standard deviation of 750 for this sample. Now, you can either calculate your standard error first and put it into the formula, or you can force technology to calculate it for you. Norm.dist, we're going to keep the 52,000, keep the mean, 57,337. This time we have our standard error instead of our standard deviation, and we're still looking at true. When we're in Excel, we're still going to use norm.dist and the same numbers as before, 52,000, 57,337, but this time for standard deviation, we can either put in 750 or we can put in our old standard deviation divided by square root of n, which is 100. So I can make Excel calculate that value for the standard error right there in the line. I'm showing you this way, and then I'll show you how to do it a different way that might be a little easier if you're just starting out. And then true. And we get something very, very strange, and I'll talk about that number in a moment. But let's go back to that standard error calculation. We had 7,500 divided by square root of n, which was 100. And we did it by hand and got 750. Now, let's do the norm.dist just like before. And this time we'll click on our standard error calculation, and that way it doesn't clutter up the formula itself, and type in true. This is another way that you can do that same problem, because notice I get exactly the same answer. Now let's copy this over onto our work. So our norm.dist this time was 5.55521 e minus 13. Okay, what in the world does this mean? Well, we've talked about this before. That e to the minus 13 just means that we're going to take 10 to the negative 13 power and multiply it by the number in the front. This is a form of scientific notation. So I'll take my 0.55521, and then my decimal point, I need to make this number smaller. That negative exponent means make it smaller. So to make it smaller, I'm going to move my decimal point to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13. Put my new decimal point there. I like a leading zero, so I put my leading zero there. Fill in zeros in all the gaps. So we have 12 zeros and then a 5 for our probability that 100 teachers will have a sample mean less than $52,000. This is extremely unlikely to happen. Our mean is 57,337, and n being 100 is a fairly large number. So a fairly large number of teachers chosen at random, we are not going to have an average less than $52,000. This is very, very small probability. But you can see the difference here. One teacher's salary less than $52,000 is almost 24%. That's a good probability you can pick one teacher at random and get a salary less than $52,000. But you cannot pick 100 teachers and expect their sample mean to be less than $52,000 with much certainty at all. That probability is way too small. So let's take a look at the next example. The average age of a vehicle registered in the United States is 8 years or 96 months. Assume the standard deviation is 16 months. If a random sample of 36 vehicles is selected, find the probability the mean of their age is between 90 and 100 months. We have our average. We're going to use the months because our standard deviation is in months. We also have an n. A sample of 36 vehicles is selected. And we're looking for the probability that the mean of their age is between 90 and 100 months. So we'll draw a picture. Average is 96. We want to know between 90 and 100. So we're looking for this probability here in the middle. Writing out our probability, since we have a section in the middle, we're going to have to do two norm.dist functions. One for 100 and below, and the second one subtracting 90 and below. So we could calculate our standard deviation before we do this norm.dist. We've got 16 months divided by square root of 36, 16 divided by 6, 8/3, whatever the decimal equivalent is of that. We'd like to use the whole number. Don't try to round it. If you round it, your probabilities will get off. So norm.dist, higher number first, 100. The mean is 96. The standard deviation, we have 8/3. And true, minus norm.dist, the smaller number, 90, and everything else stays the same. So let's swap back over to Excel. We'll calculate our standard error. We had 16 is the standard deviation divided by the square root of 36, 8/3, or 2 2/3. We're looking for the probability between 100 and 90. And notice how I clicked on my calculation for standard error both times so that I had that value in there. I didn't retype it or hard code it in like I did the first problem that we did. Do what feels comfortable to you, but again, practice in it and get used to working in the technology. And we get 0.921, 92.1%. Now this does make sense. Our standard deviation is 8/3, 2 2/3. So if I go out 2 2/3 away from 96, I get a little bit more than 100. If I go down by that much, I'm just above 90. But this is almost 2 standard deviations away. And from the empirical rule, 68, 95, 99.7 rule, 95% of my normal data will fit within 2 standard deviations away from the mean. Here I have almost 2 standard deviations, and I have almost 95%. So it seems pretty reasonable.